Okay. Ah, bueno, pues español, ¿no? ¿Inglés? Pues, ¿cómo queda la presentación en inglés? Adelante. Alright, so, good morning everyone. My name is Iñaki and this challenge will be of refrigeration system in thermodynamics. And my crew is Víctor, Berrat, Axel, Jorge Castillo, y Héctor Rodolfo Serafín. So let's introduce this sim. Basically, this challenge we were able to experiment different calculations from a cooler, basically, and we compared the air resistance with the cooler, and we did another calculations with the temperature, the final temperature, and the change over the time of the temperature. So we're gonna get into context of this, and I hope you like it.
So first of all, we know the refrigeration system. We have some materials that were very important to use in this case. For example, the styrofoam or the expanded polystyrene, the 1 kitchen thermometer, and the 5 kilograms of ice. Here in the image, we can see how we use the kitchen thermometer and we put it inside the system. Now, we will see about the properties of the polystyrene, or the properties of the expanded polystyrene EPS. First of all, we have the physical properties. The first one is low density, which tells us that it is very low weight and it is very easy to carry around, which leads us to the second property, which is the closed cell structure. As we can see in this image, taken with a microscope, we can see that they are very close one to each other. So that tells us that it is very resistant and it has the property of insulation. And the third one is the water resistant. It means that it does not absorb moisture. So it can be used, in this case, for the ice, and it is very used in the world for packaging and also for food. And that leads us to the fourth one, which is flexible yet rigid. It is very lightweight, however, it is very resistant, and it does not depend on the pressure. We also have the thermal properties of insulation and being stable. And the benefits are that the EPS maintains its size over a wide range of temperatures, from very cold to very hot, and that it also does not brittle at low temperatures and maintain its form.
Okay. And the initial characterization of the cooler box was first made that when we defined the container that we were going to use, I'm sorry. When we defined the container that we're going to use, we decided which trials we would use.
Alright, so one important question. Why the temperature was not, reduced to 0 degrees Celsius? This principle is basically because of the zero law of thermodynamics, which includes that either the temperature of the cooler and also the temperature of the air temperature needs to be in a thermal equilibrium. So it needs to be at the same temperature and it needs to reach the same amount of temperature, and it will become constant at that temperature when it reaches the thermal equilibrium. And it won't be 0 degrees Celsius because it's gonna melt over here and it's gonna reach the air temperature instead of the cooler temperature and reduce its temperature.
And here we can see the two graphics that we got when we realized an experiment with two different temperatures and in an approximate time of 1 hour and 20 minutes. Here we can see the one that was inside the cooler, that at the end of the experiment we could see that it was started to rise and it stopped basically in 13.5 Celsius. And here we can see the temperature that was outside of the cooler that at the end of the experiment was basically at 25 Celsius.
Now, with the data that we collected for the long time characterization, we got the following Excel results. First, we have a graph which shows how the temperature of the cooler suddenly decreased until it reached a minimum point, and over there it went increasing its temperature until it reached the room temperature. The room temperature also changed over the day, due to the heat, but finally it also went back to a cooler temperature where both the cooler and the room temperature reach its equilibrium. Here we have the polynomial fit for the cooler, where we get this equation over here with an R square of 0.7. And over here we have a polynomial fit degree 6 also of the temperatures of the room temperature over the day. And here we have an R squared of 0.99.
Well, the mathematical modeling using thermodynamic concepts.
First, the thing that we needed to measure was the surface area of the cooler. We did this by calculating the area of each of the parts that were inside the cooler. You can see that here is the first phase with this tree. The second phase is in here with this tree, and the part of the front and the part of the bottom were also measured, giving us a final result of 5,066 centimeters squared.
Well, now the physical concepts. Some of the physical concepts used in the calculation of this previous experiment were the thermical convection, also the thermical conduction, latent heat of fusion, and law zero of thermodynamics. Let me explain more about it. Thermical convection involves that the transfer through the movement of fluids such around as the air, which is around the environment, changes the temperature. This is the formula which represents the decrease, which is about the height, the area, and the change of the temperature, which is the first one of the cooler, and the last one, which was the same as the around environment. Then the thermical conduction. This process transfers heat through a material due to the temperature. And as already they told us, the poly theorem has a very good thermical conservation, making the change more slower. Here we can see a formula that K is the thermical conduction, A is the area, and dt over dx is the rate of x. No, the rate of t from the temperature, sorry. Then the latent heat fusion. It's the energy needed to convert ice into water without changing the temperature. For this formula, we use the heat equals the mass of the object, well, in this case ice, the 5 kilograms of ice, and then the L, which was the latent heat specific point. And well, finally, the zero law of thermodynamics. This law tells us that all the temperatures in a closed environment will reach the same temperature point at a specific time. We saw it because this box has a temperature inside, and well, this is an environment which has a different temperature. And by the time we saw on the graphic that it was different temperatures, it reached same temperature of 60 degrees.
Just to clear one thing is that this LF is basically the latent heat of, well, of fusion.
Exactly.
Then this is another formula called the heat transfer rate equation. This is a very simple equation which uses the K, the constant of the conductivity, the thermodynamic constant, plus the symmetry of all the areas that we have here of the box, times the temperature of the room minus the temperature of the cooler at a certain point over the latent heat specific point, specific value. Here we use all the values of the lines, the areas, the total area, and here are the formulas, which gave us a result of 197.6 work.
This equation is the forward up.
Exactly.
Next, with the previous formulas, we also use the formula for the separation of heat and with the respect of time. to finally get the equation comparing to the one that we get before and the one that is the differential of time of heat with respect of time, that is this one, and that uses mass. I'm sorry, and that uses mass, specific heat, and the differential of temperature and with respect of time. And we rearrange the equation with the objective of only get this term. That was the one that we were interested in.
Okay, and now we're going to talk about the temperature change. That is this equation that we deduced from the previous step. Now we're using a delta T to obtain the difference between the exterior temperature, the room temperature, and the temperature inside the cooler. In this case, making the calculations, substituting our values in the experimental data, we find that the temperature inside the cooler theoretically increases by 127 degrees Celsius per hour at the highest external temperature, that was approximately 28 degrees Celsius. Why in a specific temperature? Because this is iterative. We cannot make a calculations for all because we can take a lot of time. So we are going to use a MATLAB program for that. We're going to explain that in a moment. But at the highest external temperature, it increases by 127 Celsius degrees. And well, as it is an iterative calculation, we're going to use now discrete time steps, that is the delta T. And we are going to substitute the differential of temperature with respect to time with that formula. We're going to substitute it to find those differential, little slight differences. And this is the final temperature change formula. And now substituting and rearranging the terms so we can find that temperature that is added to the previous one. So we can find that temperature that is the difference. These are our data, and substituting all that data in the equation, this is to find the total heat capacity, considering all the elements, for example the air and the ice. We obtain a value of 10,588 joules per Kelvin. And well, with all the values, we find that, for example, temperature 1 is 17.89 degrees Celsius. That it means that after the first 5 minutes, because we use a delta T of 300 seconds, the temperature inside the cooler has dropped from 18 degrees Celsius to 17.89 degrees Celsius. This happens because the room temperature is lower. Indeed, in that moment it was of 11 degrees Celsius. So the heat is leaving the cooler, causing it to cool down slightly. Why this happens? Because the temperature change depends on the difference between the cooler and the room temperature. This provokes that if the room temperature is higher, then the cooler warms up this over time. If the room temperature is lower, the cooler cools down. Also happens that if the room temperature increases later in the day, also the cooler temperature will increase, and the cooler will gradually reach equilibrium with the room temperature, as we saw in the graph, that it reached when it was 16 degrees Celsius. And this is the MATLAB program that we use to, as I mentioned before, this requires iterative calculations. So to model the full temperature evolution over the different hours, we use 16 hours in our measurements. We need to report the calculation many times, so manually computing each step was inefficient, and we use MATLAB to automate the process. This is the code. These are all the constants that we use. These are the initial conditions. In this case, we use a time step of 5 seconds. And this is the loop in which it determines the temperature for each data measured.
And here we have the parameters of time, of seconds, and temperature in Celsius, and the evolution of the temperature over time. Here in the graph we got from MATLAB.
And well, with this study, we investigated and proved the use of a styrofoam cooler with ice to maintain coolness over time. It predicted a temperature increase of 127 degrees Celsius per hour at room temperature, but then ice melting slowed down warming. So we use MATLAB to automate these temperature changes and compare the predictions. So the results confirm passive refrigeration effectiveness in keeping temperature-sensitive items cold, making it useful for the storage and transport. And thank you very much. That was all our presentation.
Thank you for your attention. Thank you for your attention.
in one of the questions about heat calculation,
Which one?
Which one? In which one of those?
maybe
This one?
In that one.
no, the next.
The next one?
That one?
That.
Oh, okay.
All right.
About theta, the increasing time, why did you choose 60? It's
60
seconds.
Yes, no, it was the 60 minutes, so it can be used in 1 hour. So as we mentioned that, it's an increase per hour, so the step was of 60 minutes.
Every 60 minutes.
Yeah.
Okay. Because the conductivity, what are the units for the conductivity?
The units?
Yes.
Well, we mentioned in the data, where the list was all the data, there were the units.
In that one, yeah.
Yeah, and that one.
Because it's in watts.
Well, yes, this first calculation we
So
measured
you
in watts.
have to use seconds as time. Or
Oh, it needs to be in seconds instead of minutes?
No, what's per second?
No.
No.
okay,
And the units?
Just a question, why you use the 60? You have to take care about the units of
So we should have multiplied by 3,600, no? To convert it into seconds.
But I think this value just, well, it validates the model because yes, from each hour and now a Celsius of
Yeah.
of 1 degree
Okay.
approximately.
Yeah, 1 degree each hour.
Yes, we have a different step.
Okay, so 1.127 degrees, what is?
The rate of change of the
The increase of the temperature, but inside the cooler.
Yeah, inside of the cooler.
Per hour? Each hour or?
Yes, in this case, yes.
Yeah, each hour.
Each hour.
Per hour.
Yeah.
Okay,
Yeah,
just
the
to
calculation.
declare it,
Yeah. Okay.
that this delta T is a rate of increase for a certain time.
Yeah, okay.
Yeah.
Okay.
Yeah.
Okay. In the last plot,
And the last one. And
the question is
the
because
Which one? This one or the later one?
right?
This
Yes,
one?
The increasing temperature is very fast. So maybe have to check something because in your measurements you spend how much hours?
Yes, but the thing is that we use a different step here. We use a step of 5 seconds. Just it's the
Yeah.
to see the slight difference, the differential difference.
It's the difference of the step.
Yes, this is just in 5 seconds. What happens in just 5 seconds?
Just every 5 seconds.
Yeah.
That's how it increases.
Okay. In the plot, in the experimental plot,
En el código.
The bigger graph.
¿el one?
La más alta.
En el.
yes. Claro.
No, el anterior. El anterior. Ahí está.
How do you believe affect the external temperature in the internal measurements?
Well, as we mentioned,
Because you measure what, that's good. You also measure the external temperature. So how does affect the external temperature?
Because of the thermal conduction, when it has a greater temperature, the
No, it's because of the thermal conduction. Because of thermal conduction, as the air has a temperature of, well, we saw that this temperature of the environment affecting the air, and the molecules of the air are like crashing or making collisions with the cooler, and well, the temperature inside the cooler is different, and this little crash of particles changes the temperature, and that's why we see an increment of temperature inside the cooler, and the outside of the cooler is just the environment, and it depends on the example.
It's a relation. The higher the temperature of the ambient, the greater will be the rate in which this one tends to go to the same temperature.
Yes, and when the room temperature decreases, well, it just decreases the warming of the inside temperature of the tube.
And also, as you can see, it goes over here to get into constant temperature over here.
Oh, but
We're
that's-
reaching a terminal equilibrium.
Okay. I highly recommend to include the page numbers.
Okay.
It's easy to move around.
Yes, of course.
Yeah.
The other point is, when you load some information, please make sure the audience will be able to read the information.
Oh, yeah.
For example, it's impossible for me to read the axis, the numbers of each
Yes.
point.
yeah.
So,
Yes, it's because the graph has a lot of data, so
Yeah,
the point is going to be a
Yeah, how much we
you can
would be able to
increase
compress it.
the full size.
Okay.
Absolutely.
Yeah. The next time we're gonna do our best.
Please, can we move to the slide with the thermical convection is defined
Which one?
in this slide?
That one.
What's the meaning of thermical convection?
It's a form of heat transfer.
It's similar to the thermal conduction, but the difference between those one is like is that the thermal conduction needs to be object. The object needs to be next to another object. It's like touching them, and the convection just is not that range. It could be like this, and it will be thermal convection. Also, similar concept of. This has a higher temperature or lower temperature, and this has a different temperature from here. This one is changing the temperature because of the distance.
And also, for example, in this case with the ice and with the system we have, for example, the ice, we know that it's not always like a solid. It also gets liquid from time to time. So with the little liquid we have, we can use Newton's law and we can check the heat transfer between the air or about within the system and with the liquid we have inside of it.
To be honest, I never listened before about the thermical convection. I know about the thermal.
Yeah.
Well, it was,
exactly.
it was maybe a translation mistake.
I'm sorry about the terminology.
Yeah.
But yes, about it.
Okay, thank you.
Yeah, no worries.
No, thank you.
Exactly. No, thank you for listening so much.
Thank you to you.
Thank you so much. Well,
¿Eso es todo?
That's it.
that's it. All right.